Okay, I'm gonna restart this after that elastic band fiasco. Stefan and Callum. There's a part of a male human being's brain, even though today it's my birthday today. Do you know how old I am?
50.
Correct. You should have said 40 though. Your grade would have gone up. There's a piece of a male human being's brain that is always in elementary school. It'll always stay there. Even I wanted to like shoot it back at him, but I won't do that. Okay, we're gonna learn about circuits. Here's some stuff. So we didn't do this last chapter, but we learned a little bit about static electricity really quickly, right? So what's the difference between static electricity and current electricity? Nothing. Surely you know this. Okay, it's a good thing we're doing this. What does the word static mean? Yeah, that's right, Benji, thank you. Lizzie, say that again. Yeah, one's kind of flowing through the wire, as Lizzie said before, and the static is just, it's a movement of charge, but just to one place and then it stops. So you rub the balloon on your hair and you stick it to the wall, it's just an attraction. It doesn't keep going around the loop. And current electricity is the flow of electrons around that loop. And I think that's your first little blank, right? Current electricity is all about the flow of electrons. Tell me turn to the person beside you and tell them something about an electron.
There is like
Okay, tell me one thing about an electron. Negatively charged, good. Anything else? It's very light, isn't it, Keon? Yeah. Is it a lot lighter than a proton or just a little bit? It's a lot. It's 1,700 times lighter than a proton. About. And then I heard Angelo talking about positrons. That's interesting. Where did you learn about positrons?
YouTube.
Oh, cool. You should be in IB physics. It'd be fun. It's hard though. Okay. So a conductor allows electron flow and an insulator impedes electron flow. And so we use conductors for current electricity. So all the wires that we have. What are the wires in this classroom made of, do you think? Liz, you say that again.
Copper.
Copper, good. Yeah, she said it first. You mind your own business. Tell me another conductor other than copper. Gold is actually really good. I think it's the best. Yeah, so expensive though. Anything else? Iron would conduct, yeah. Silver is really good. Why are these wires not made of silver? Too expensive. Why are they not made of iron? Because iron rusts and it's brittle, so you can't bend it. Copper's nice because it's malleable. You can like twist it around. And wires always used to be aluminum, and still the big ones out there are still aluminum. Aluminum is another really good conductor. Okay, give me an example of an insulator. Water is an interesting one. So pure water is an insulator. But if you used tap water, it would be actually a good conductor. What's the difference?
Distilled water has ion charge.
That's correct. That's correct. Let's give Angelo a call. It's on it. It's on it. Yeah, so tap water has these ions in it. It has calcium and magnesium and all these little metals that will go and they'll fly through water. But pure water doesn't have any charge in it, really. The water molecule is polar, but they just kind of spin around. What's another really good insulator? Kiana? Carbon is a pretty good insulator, yeah. Sam? Rubber is a good insulator. Yeah, the soles of your shoes, or if you're an electrician and you have a tool like this one, see how the handles are coated in rubber? That's because if this is an electrical tool, you don't want to get shocked if you're working on something with power in it. These people were fairly unkind though. They left the end metal, so he's gonna get shocked anyway. Fluoride. Oh, that's interesting. Probably yes. Yeah, that's good, Artin. What about glass? A window. Glass is a really good insulator, and it's used a lot in electrical things to insulate. Plastic is also a pretty good insulator usually. Sam? Wood. Yeah, wood can be an insulator for sure. If it's wet, that's bad. But okay, so knowing conductors and insulators, what is the air? Is the air a conductor or an insulator? It's interesting because kids usually say conductor, but it's not. It's an insulator. Why? How do you know that the air is an insulator, and why do kids like you think it's a conductor? Say that again, Sam. Because clouds, yeah, and what comes from the clouds or to the clouds? Lightning. And so you think, well, air must be a conductor because the lightning is jumping through, right? But here's the thing. If air was a conductor, there would be no lightning, because the charge would just move through. It wouldn't have to jump across. So lightning is actually kind of proof that air is an insulator. There's electricity in this room right now, right? In the lights and the projector and everything. If air was a conductor, what would those charges be doing? They would be shocking us, right? We would be like, it'd be because they would all be wanting to get to ground, and they would go through you to the ground, and it would be a real pain if the air was a conductor. So the air is an insulator. Okay, the flow of charges is defined by the specific quantity current. So current is I, capital I. What's the big Q? Lawrence, what is Q, do you think? Okay, that's all right. Just thinking. MC, do you know? What's this Q? Say that one more time. You're not sure? Okay. Angela knows and Kiana knows. Lucy, do you know? Okay, this is good that we're doing the right thing. Edward, do you know? Very good. Let's give him a golf clap. He wasn't sure. There he is. So we call this charge. And Edward's right. The unit is coulombs. Okay, and what's T? Yeah, time in what unit? Yeah, time in seconds. Okay, so if current is charge over time, what does that mean? Like, this is the math of it, but what does it mean in the real life? That's right, Kiana. It's how many electrons are going by per second. So with my analogy of the trucks, what was a truck? Good. Lizzie, thank you. So 1 truck is 1 coulomb. And what is a coulomb? It's a number of electrons, yeah. It's a big number, right? It's a bunch of electrons. So the more trucks per second, the higher the current. Okay, good. And the unit of current is amperes or amps. And you guys know about those now because you've measured them in your own circuits. So current will not flow unless you have 2 things. You need voltage, you need some push, you need energy in the circuit, power, and you need a complete circuit. You need a road for the trucks to drive around, and the trucks need fuel to push themselves around the road. I got lazy with this one, I'm sorry. What happens if you have voltage but you open the circuit, so you make a break in the circuit?
Spark.
You might have a spark if it's close and if it's enough voltage. What if you break it and you hold it far apart? Will there be any current? No. No current. So you need a complete loop for the current to flow. I got lazy with this electrical outlets here. What's the source of power from our electrical outlets here? Does anybody know? What actually makes the energy, where do we get the energy from that comes out of your plug?
BC hydro.
Yeah, for us, almost for sure, it's a hydroelectric dam. Now, it could be in certain places. It could be, I think Lizzie said a wind generator. So it could be from that, or it could be from a coal burning power plant. If you're in the States, it most likely would be that. It could be a nuclear power plant. We have a lot of those as well. But so for us, I do want you to think beyond electrical outlets. Where does the energy come from? For us, it's a hydroelectric dam. Okay, we good? Okay, so current depends on 2 things. It depends on the voltage. So voltage is what's pushing the coulombs around the circuit. They're pushing the trucks around the road. And you can think of that as the fuel in the truck or the energy loaded onto the truck. And then the resistance affects current as well. So the resistance is how wide the road is. So if the road is wider, does that mean resistance is less or more? Good. If the road is wider, there's less resistance. Easier to drive, right? says current through a circuit is directly proportional to the voltage. What does that mean? What does directly proportional mean? Anybody know? Say that again, Lizzie. Yeah, it's a good way to say it. What does it look like? What does a directly proportional graph look like from math? You guys remember that stuff? You probably did it in grade 8. Well, let me ask you this. You guys know this from your lab. If I were to graph voltage versus current, what would the line look like? Yeah, Addie's going like this, so it's just straight up, right? So it's linear and it goes through 0. That means directly proportional. So what happens if I have a circuit with a certain resistance? And this could be a question on a quiz, hint, hint, nudge, nudge, wink, wink. If I double the voltage, what happens to the current? Thank you, Lawrence. If you double your voltage, your current's gonna double as well. What if I triple the voltage? Then you triple the current. What if I cut the voltage in half? Then you cut the current in half. So it's always the same proportion. What is the slope of this line? Good. Thank you, Kiana. This slope equals resistance. How would I go about changing my resistance then? Okay, yeah. What would I have to do in real life to change the resistance in a circuit? Say it again. Okay, if I change the voltage, then my current will go up, but my slope is still the same. So what would you have to do to your circuit to change the resistance? Okay, if I change the current, if I double my current, my voltage just doubles, right? So how am I gonna actually do it?
You can change the wires.
That's right. That's right, Kiana. You have to actually physically change the circuit. The resistance of a circuit is kind of defined by what is actually in the physical circuit. So if you want to change the resistance, you can't just up the voltage or change the current. You actually have to change something in the circuit. So what if I have a simple circuit and then I add another parallel branch? Turn to the person beside you. So let's say I had just this simple circuit going around. And then I add another resistor or whatever as a parallel branch. Turn to the person beside you and explain to them, if I add this extra branch, does the resistance go up or does the resistance go down, and why? Tell the person beside you.
So we're adding another resistor. Why do I think it takes more time to do it? So, what is it?
Okay, tell me the answer. If I add another parallel branch, does my resistance go up or down? It's interesting because intuitively you want to say up because you're adding another resistor, right? But if you're a truck on the road and you're waiting for traffic to go over the bridge, and then someone builds another bridge beside you, is that going to make traffic better or worse? It's going to make traffic better. You got more ways to go, right? So adding another branch here actually lowers the resistance. So if your voltage is the same, you got the same number of batteries, what's going to happen to your current? If I give another bridge for trucks to drive around, what's going to happen to my current? Is it going to go up or down? Think about if you're sitting at Lionsgate Bridge and traffic's backed up, and then somebody builds another bridge, just poof, Harry Potter's it into existence. Are you gonna see fewer trucks going by or more trucks going by? You're gonna see more trucks going by, right? Sam's going like this. Because you got more ways to go. So traffic's gonna open up and it's gonna be moving faster. So adding another branch makes resistance go down and current go up. And graphically that looks like this. Your slope is lower. And so for every volt, you get more current. So try to think about that. I'll ask that question on the quiz too. So current through a circuit is directly proportional to the voltage, and current is inversely proportional to the resistance. And all that means is this. Oh, I'll make that clear what inversely proportional is. If you don't like the trucks, there's another analogy of a river. And if you flip your page over, I think I just typed it in there. So in the river, the amount of water going through is your current. And if you make the river steeper, that's like a higher voltage. So what's gonna happen if the river becomes steeper? Yeah, Angela's going, so it's like more, you go faster, you have a faster current. You have more water going by, you have a bigger current. The resistance is kind of like how wide the riverbed is and if there's rocks and stuff in there. So if you have high resistance, the water's going to be backed up and it's not going to flow as well. So just another kind of analogy. So this is I'll share these slides with you so you can read these later if you're studying or whatnot, but just kind of another analogy if the trucks don't make as much sense. Okay. Voltage. If you're one of the people, and I do not blame you, who's been thinking, I don't understand what voltage is, it's okay. It's kind of a hard thing to understand. Voltage we call potential. So these two words really mean the same thing. Now, you guys know about potential energy, right? So if I have a stapler and I hold it in my hand, how do I increase the potential energy in this stapler? I lift it up, right? And if I know the mass of this stapler, I can do MGH and I can calculate the potential energy I've added, yes? Okay. Now what if I said, I want to know the potential, but I don't know. I'm going to take the stapler out of my hand and I'm just going to say, if I lift it 1 meter, how much energy am I going to gain per kilogram of thing that I lift? So you're not going to get the full amount of joules. You're not going to be that specific because you don't know how heavy the thing is that you're going to lift. There's just an empty hand right now, right? But you could calculate how many joules per kilogram of thing that I would lift, right? If you do the math, you'll find it's 9.8. I would get 9.8 joules per kilogram if I lift it 1 meter. Does that make sense? So it's not quite energy, but it's energy per kilogram. This is the same, but it's not energy per kilogram, it's energy per coulomb. That's really what a volt is. It's not quite energy, it's the energy per coulomb of charge I push through. If you like the trucks, it's the energy we load onto the back of the truck. And if you like the river, it's the steepness of the river. It's how much energy you're giving per coulomb of charge going through. So a volt is a joule per coulomb. Current is flow of electrons, which you guys know. The unit is amps. And that's a coulomb per second. And of course, the resistance is how difficult it is to flow. And the unit of resistance is ohms. So this little squiggle thing, that's a Greek letter called omega. And this is Ohm's law. V equals IR. This formula is on the wall. It's at the back there, but it's hard for some of you to see it. I will always give you this law. You don't have to remember it. Although it's pretty simple. So of course this turns into V over I is equal to R. And that's why the slope of this graph is the resistance. Because slope is rise over run, right? So voltage over current gives you your resistance. How long have I been going here? Long enough, probably. I'm gonna give you a little break. What is that? What does the clock say? 12:30. Okay. It's sunny outside. Let's crack the door and go for a walk. You have 5 minutes to stretch your legs and clear your mind. I'll start again at 12:35.